Good morning and welcome to Physics 11. We're taking a look at forces. This is the second lesson, and we're going to be taking a look at gravitation, but what's called universal gravitation, not just something that's happening within a uniform field. So let's get my screen set up properly, and then we can get going. And there I appear once again. Excellent. So here we are, Physics 1, Week 1, Lesson 2, Universal Gravitation. So yesterday, you listened to my video where we were talking about this gravitation, this first equation for gravitation. And sometimes I'll even talk about this as being the force of gravity and put a little g after it just to differentiate it from what we're going to talk about today. If you remember, little g is what we call the gravitational field strength, not gravity. And it has the value of 9.8 newtons per kilogram, and that's the same thing as 9.8 meters per second squared, because this, as I mentioned, is how we actually measure the value of little g, taking a look at the acceleration. All right, so this is what we did yesterday. We went over there, gave you a few questions to do. Assuming, you'll ask if you have some questions, I'm sure. Now, there's this story that, there was this tree, and in this tree, we should change, there were some apples. And that under the tree, there was Newton. And he was sitting there one day and minding his own business, maybe even eating an apple. And an apple came bonked on his head and fell to the ground. And Newton was surprised. And he thought, why did the apple fall? I got to stop writing. Why did the apple fall? Well, the apple was attracted to the earth. The apple was above the earth. It was suspended. When the stem broke, then the apple fell because the earth was pulling it in. So the earth attracted the apple. But if the earth attracted the apple, sort of like a one-handed fisherman. You've heard of the one-handed fisherman? Yeah, he went out fishing and caught a fish this long. There's no reference to it. There's no how long was that. So if the earth was if the apple was being attracted to the earth, was not the earth also being attracted towards the apple? And this was his conundrum, or they began thinking about gravity and how gravity worked. And he came to the conclusion that every object, every mass attracts every other object. So while the earth attracts you and holds you to the earth, you're also attracting the earth up. But it goes beyond that. That when you walk towards, say, your mother or your father, you have mass, your father has mass, and there is a force of attraction that pulls you towards it. But we don't see that. That's the strange part about it. But he began talking about this and trying to understand really what this means. And he really began talking in terms of what we call proportionality. And one of the proportionalities is to say the force of gravity is proportional to, and we use the symbol alpha to mean that. And if we're taking a look at two objects, it's going to be proportional to the mass of those objects multiplied together. So that if we increase the mass of one of these, there's going to be an increased force of gravity between them. How do you see that? Well, think of a box. If you've been to the grocery store and you've seen those crates, and in the crates they got jugs of milk. And let's say there's one jug of milk in that crate. They got the hatchwork on them and so on. Well, you know that there's a certain force of gravity that is pulling that milk crate down. And you have to exert a certain amount of force to lift it up. Well, now let's put in a second jug into that crate. Does it take more force, less force, or the same force? Well, it takes more force. The mass now of the crate has doubled because we have two jugs in there. And so we're going to take 2 times the mass, the second mass, 2 times the jugs to lift that up. Well, what if we put in 3 jugs or 4 jugs? Then we're going to have 3 times or 4 times the original force of gravity to lift it up. So that just is one way of taking a look at what we mean by this proportionality, that the force is going to be proportional to the product of the masses being multiplied together. And as masses increase, the force of gravity increases. Something that's really heavy has a large force of gravity, and so it's really difficult to lift up. And that's perhaps an easy way, or perhaps the best way of taking a look at this. But let's go back. What about, well, let's consider the sun. The sun is big and has a big mass, presumably so. And here we are over on our Earth, and we feel more force here than we do here, but this is a huge mass of the sun. Why don't we feel that effect? Why don't we have that force? Why is it that we don't have to, tie ourselves down at noon, hanging onto the ropes to keep us from not flying off towards the sun? Well, this was the other proportionality. And he said the proportionality, that gravity is proportional. This is supposed to be a big G. Gravity is proportional to the distance 1 over the distance squared. And so that as the distance increases, the force of gravity actually gets less. Imagine if that wasn't so. Like, the mass of the sun is huge compared to the mass of the Earth. Like, thousands of the Earth would fit within the volume of the sun. And so you can think that the gravitational attraction of the sun would be many, many more times greater than the attraction of force between us and the Earth. And so, yeah, we would be torn off of here. But we've got this proportionality, this relationship. Yeah, to be honest, I'm not sure how much Newton did, perhaps in experimentation with this, and whether it was just thinking. Galileo did some work within this, I believe. But it's kind of interesting sometimes. There's a lot of Newton. So Carmpreet said, "Sir, you're kind of similar to Newton. You're both nerds," or something like this. And I took that as a compliment. But Newton was very much a nerd. He gave him the idea of the story of laughing once in his life. For him, for people that are so smart, for them to be thinking about some of these things, they can come up with some of these conclusions, and they can go through the thought processes for them. I mean, it was really quite quite fascinating. But we have these two proportionalities, or the proportionality is the force of gravity due to the masses and the force of gravity due to the distance between the masses. What happens to the force of gravity when two objects doubles? It doubles. We just talked about that. What happens to force of gravity if the distance between the objects double? All right, so here we have two objects. We'll call it M1, M2, and we're going to say that we have this distance of 1 between these. Okay? And so then we're going to take this and we're going to bring M2 now over to here. And so what we've done is that we've doubled the distance, and so now this is an extra one here. We can think that they are now 2 units apart. Okay? So what we're saying in terms of this proportionality, the force of gravity will be 1 over the distance squared. So we're saying, well, the distance is not just d, it's now 2d, and that's going to be squared. And we can work out this denominator here and say, well, that's 1 over 2 squared times 1 over d squared, and 1 over 2 squared is equal to 4. So that's equal to 1 over 4 times 1 over d squared. And so what we can see is that our force of gravity is 1/4 what the force of gravity was. This is what our force of gravity was. F was. There we go. We've doubled the distance, but the force of gravity is going to be 1/4. If we triple the distance, it's going to be 1/9. If we quadruple the distance, it's going to be 1/16. And so the force of gravity drops off quickly as we increase the distance between. And that's why the sun, incredibly huge, has very little effect on us. Okay, let's continue on. So Newton gave us what we've come to call universal gravitation. And this can be expressed as a proportionality, the force of gravity, and really we're just taking the two proportionalities and putting them together. M1 times M2 over the distance between the two masses squared. This is the force of gravity, and we're just pulling these things together. But in order for us to do calculations, we can't really do this, not in terms of absolute calculations. We can talk about relative changes of doubling the mass or doubling the distance, but we need this to be an equal sign, not a proportionality. So what we need is a constant. We need a value that relates the force to the masses and to the distances. And so the constant we call capital G. We have little g for the universal or for the gravitational field strength. Here we're now going to use capital G. And so we can express this equation then. Capital G, our force of gravity will be equal to capital G M1 times M2 over d squared. So this is our equation that we use for universal gravitation. Any two masses anywhere in the universe will have a gravitational force towards the other. There's a gravitational attraction. This value of d can get huge. But there will always be a force of gravity. The only time the force of gravity goes to 0 is when d goes to infinity. That's the technical term. So every other particle is attracted to every other particle. The force of gravity just falls off quite quickly. So What is this value of G? Well, G has a value of 6.67 times 10 to the negative 11. This is a very, very small value. And the units for this would be newtons meters squared over kilograms squared, just to be technically. So that's our universal gravitation. Now, the interesting thing is that it took 200 years for this value of G to be determined. I guess they just never did much calculations back then. But it was a fellow named Henry Cavendish. So Newton lived in the 1500s, and then Cavendish lived in the late 1700s. So it might have been almost 300 years. And what he did, well, he continued, I was just reading about this, that someone else began the experiment and I think died, and it got passed on eventually to Cavendish to do it. Now, it's really quite interesting. And when you think about the day and age, this is the 1700s. There was not technology. The Industrial Revolution had not happened. If things were being made, they were being made by you, or maybe you'd hire them out. Anyways, what he did is that he suspended two masses that were about 1.8 meters apart on a thin wire. And this thin wire could twist. And so the sort of like in that infinity clock. Remember at school, I've got that infinity clock. It has a face and has these posts, and then underneath it's got this thing of four balls, and it spins one direction, and then it spins the opposite direction. And it's the clock. It's a clock. You might even have one in your own home. But this is a torsion. There's a torsion piece of wire that expresses the torsion, has a twist to it. So it spins one way and stops, and then spins the other way. And it just keeps spinning, going, keeps on spinning back and forth. And that's what the escapement for this clock is, and they run quite efficiently. So anyways, with Cavendish's experiment, he had this thin wire, and I think this is about 6 feet tall or more, and he had this bar going across where he had these two pretty heavy weights at either end. They're lead weights. And then what he would do is that he'd bring another mass close by, actually two masses close by on either side. And then what would happen is that there would be a force of attraction between these. And so there would be a twisting that would happen because of this. And by measuring the twist, he could measure how much force there was. Okay, so now he's measuring the force. How does that get us to a value of G? Well, let's look at it this way. We said that F is equal to Gmm over D squared. On his experiment, he could measure the distance. He knew what the values of the masses were, and he had just measured the value of the force. So we can rearrange this to say G, well, that will equal our force times our D squared over M and M. And in this way, they could come up with the value of this constant G. And once they knew this constant G, then they knew the mass of the Earth, and they could take a look and know the mass of the Sun, and take a look and know the mass of the planets. It's really pretty fascinating what they could do. And the crazy thing is that it took 200 years. But that maybe it's crazy that Newton thought of this 200 years before that they were able to actually come up with a value for this. But that's sort of the brilliance of Newton and the amazing work of Cavendish. Now, I've explained this really rather simply, but he would have to account, well, he'd have to build it inside a big box so that air currents wouldn't get on there. Because the amount of movement that he was seeing in this twisting was like 4 millimeters of movement over like 2 meters of distance. very, very small. The force of gravity is extremely small, but he was able to do it. And, there could have been other reasons for the force of attraction. There could have been static reasons, a positive and negative are attracted, so he had to account for that. And there could have been some discontinuity between the forces, and so he'd have these two masses here, but he could rotate them and apply them to the other side of the masses and measure the amount that it twisted back the other way. So in this way, Cavendish created a very sensitive device with which he was able to actually measure these values, this value, which is incredibly, incredibly small. All right, so let's make use of this then. What is the force of gravity between a 60, let's draw a diagram, 60 kilogram girl and a 70 kilogram guy? Let's put smiles on them. Okay, so we know that they are 1 meter apart, and that's from the center of gravity of an object. So just to point this out, so if we have two masses and they're spheres, the value of distance is not this. That's not it. It's the value from the center of gravity. That's the distance that we're going to use. So I'm not sure that will necessarily come up, but just recognize that's the case. All right, so we know M1 is equal to 60. We know M2 is equal to 70. We know the distance is equal to 1.0 meters, and we're wanting to calculate the force. All right, so F is equal to G M1 M2 over D squared. Well, G, 6.67 times 10 to the negative 11, 60 kilograms, 70 kilograms, and then we've got this 1.0 meters squared. So this is where you pull out your Casio FX260 Solar. I know, I'm sorry. But hey, this could be my last year saying this. This is going to be my last year saying this. And you guys are going to have to carry on. So 6.67 times 10 to the negative 11 times 60 times 70 divided by 1 squared equals, and the value of the force that we get is 2.80 times 10 to the negative 7 newtons. Diddly squat. And so what is the conclusion? What does that even mean? Well, it's a statement that Einstein made. I believe it's attributed to him, and I believe I read his biography, and I believe it was corroborated in there. And Einstein said that the force of gravity cannot be held responsible for people falling in love. Put a heart around there. Oh, isn't that sweet? But you can't blame gravity. The force is just too small. I know that there's one question that I've had students do in the past, and we'll see whether we do it or not. And what it did, the question was for a pregnant woman who's giving birth to a child. What has a greater force of gravity on that child? The doctor who's standing right there delivering the child, or Mars, the planet Mars? Well, it turns out the planet Mars has a greater force of gravity on the newborn baby than the doctor does, and the doctor's right there. Force of gravity is a very, very tiny value. All right, so here, let's do another one. What is the force of gravity between two 2,000 kilogram cars? Those are heavy cars, 2.5 meters apart. So we've got one car, and we've got the other car. I know, I just like drawing. I think you guys would be disappointed if I didn't draw. There's the other car. And we know from the center that they're 2.5 meters. And we know that they're both 2,000 kilograms. So again, we just set these things up. F is equal to G M1 M2 over D squared. F is equal to 6.67 times 10 to the negative 11 times 2,000 times 2,000 divided by 2.5. This is meters. And we're having to square the value. Oh, I'm sorry. 2.5 squared. There we go. And again, pulling out Picasso FX 260 solar. 6.67, 10 to the negative 11 times 2,000 times 2,000 divided by 2.5 squared equals. Wow, this is much, much larger. It has a value of 4.3 times 10 to the negative 5th newtons. Diddly squat. And as we point this out, I mean, you might say, well, really, how much is a newton? And so let's just draw a hand here. And if you were to put 2 golf balls into your hand, then you would be experiencing the force of approximately 1 newton. So that's what a newton is. We're talking to something that the force is 10 to the negative 5th. Again, very, very small. So what we have now is F is equal to mg. We have F is equal to g m, let's go 1 and 2, over d squared. And how do these compare? Well, on the surface. So even if we climb to the top of Mount Everest, the force of gravity is still approximately the same. There's very little difference in change, or very little change, in the force of gravity. So if we're dealing with things that are on the surface of the Earth and so on, well, we're going to be using this equation. This is when we're dealing with planets, when we're dealing with stars and so on. Then we're going to use this equation to calculate the force of gravity between those. So planetary distances, or we're in the surface, are just on the surface of the Earth. That's how these two equations sort of get used. So coming back to this, I'm assigning you a few more questions, 7 to 13. Today is Wednesday. I'm not going to give you any new questions tomorrow on Thursday. It's a long weekend. So I really would be expecting these questions to be done for next Tuesday, if that makes sense. And some of these concepts are a little bit difficult when you're dealing with proportionalities and so on. I know, to be honest, I know when I was in school, I hated proportionalities. Don't give me proportionalities. I want something I can plug into my calculator. Give me numbers, not these conceptual ideas. Work through them. Like now, I think, maybe I'm older, proportionalities, they're cool. They're interesting, how we can analyze these things without actually having to do calculations. Anyway, so no questions, no new questions on Thursday. Next week, then we'll talk about friction. That's the next topic within this these forces. And but I just want to say that tomorrow, if you do have some questions, hey, drop by, particularly during class time, which is 11:17 to 12:34, and ask some questions, and I don't mind going over some. I keep on hoping for faster internet, and that's not here yet, but hopefully it will be soon. Anyways, it's like 10:30 at night right now, and I'm just doing this, and I'm tired, but I enjoy talking with you guys, even if you're not here, and this is strange. And as I'm talking, I'm thinking of Compreet, and I'm thinking of Megan and Kanisha, and Haley at the back. Haley, get off your phone. Pay attention. And Ava, you're not even paying attention, I'm sure. You're probably making more spaghetti. I miss you guys. And I really enjoyed chatting with you guys the other day. And I hope you guys do well. Keep up. As you have questions, please check in. And Kaylee, thank you for checking in and doing the test. And Ty, thank you for checking in. I have not heard a word of you, and so I'm glad that you obviously listened to the last lecture and you did the test as you needed to. And hopefully you were listening to these lessons as well. All right. Yes, Tim and Maya, you guys too. Like, have I forgotten anyone else? Well, there's Brody and Armand and Peyton and and Amanda Richter. Yep, sitting up in the front. Amanda, you're always so quiet, and now you're even quieter. I can't even hear a word you're saying. But I hope you guys are doing well. And, stop by and chat. Drop me a note. Let me know how things are going. If you have questions. And some of you have been wanting to know about a retest. And, we'll set that up for next week. We'll make it available. And probably what I'll do is I'll give you a link. And you can do it when you're ready. But I really suggest that if you did not do well on the test, ask some questions. Get some things worked out, okay? Because I don't feel it was really a difficult test in and of itself. The review was much harder, much more difficult. This was the standard that you were to be tested at. All right. Anyways, we'll talk to you, I'm sure. Take care. I got to turn this off. And I come over here. And goodbye.